Hey everyone, welcome back, and today let's solve Leetcode problem 139 titled Word Break, a very common interview question at FANG companies. So we're given a string S and a dictionary of strings word dict, and we need to return true if S can be segmented into a space-separated sequence of one or more dictionary words. And note that the same word in the dictionary may be reused multiple times in the segmentation. That's also pretty important to note here. So in example 1, we have the input string S to be Leetcode, and we have the word dictionary to be an array of strings, Leet and code. Why do we return true here? Why? Because Leetcode can actually be segmented or split, or rather partitioned as Leet and code. And notice how Leet is one of the words in our word dictionary input, and so is code. And since, well, Leet in our input string S is in the word dictionary, and the remaining characters code is also in the dictionary word dict, we can return true, because the whole input string can be segmented using some of these, if not all, or if all, when needed, words from this word dictionary. Okay. In example 2, we have the input string S to be apple, pen, apple. We have the word dictionary to be apple, pen. Why do we return true again? Again, we can use apple and pen, or the words in our input word dictionary, as many times as we'd like. We have them an infinite number of times, right? We can return true. Why? Because it can be segmented, our input string S, as apple, pen, an apple. And notice how apple is in our word dictionary, and same with pen, and so is apple again. We're just reusing that same word from our word dictionary, and we're allowed to again use, or rather reuse, a dictionary word as many times as we'd like, as it says right here. Now, finally, in example 3, we have the input string S to be cats and dog, and we have our word dictionary to be cats, dogs, sand, and cat. Why do we return false? Because, well, we can make cats using our cats word from here, and we could make dog using our dog word here, but we'd have two extra letters. We'd have A and N. And sure, you may be wondering, okay, we can make sand here, but then we'd have og remaining, and so same with, we can make cat, and we can also make sand. But we can't make og. Og isn't a word in our word dictionary. It's simply an outlier. And since we can't really segment our input string S into separations of words solely formed or present in the word dictionary, we'd have to output false, because regardless of what combination we try, we're going to have at least one or two characters remaining that we haven't used or segmented in using some words in our word dictionary input. And so for that reason, we'd output false. So with that out of the way, I will give you guys a few seconds to kind of just go over this problem in your head and think of a valid solution, and then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so if you guys haven't realized yet, this is actually a dynamic programming problem. But why is that? Let's kind of understand why we actually need to use dynamic programming to solve this efficiently. Why? Because as you can see, this is a pretty complex problem, right? We have to kind of segment or determine if our input string S can actually be segmented into this word dictionary, right? How do we actually solve this kind of efficiently? Right, we simply have to break down this complex problem into simpler subproblems, right, or subcases where we simply check, is each suffix of S, can it be segmented using one of the words in our word dictionary? If it can, we can simply move on and solve these subproblems step by step or incrementally. Okay, so when we determine if a substring or suffix from S at index I can't be segmented, we have to rely on previously computed results for, well, other suffixes like S at I plus the length of the current word we're looking at for various words and indexes or indices in our word dictionary as we iterate through our input string S. And this is going to lead to repeated subproblems where the ability to segment a particular suffix can depend on multiple prior computations, right? Where we have to kind of compute multiple or previous prefixes to rely on them to compute the current prefix, right, at the current index I, right? So with that out of the way, let's just go ahead and dive straight into the code here. So how would we kind of solve this efficiently, right? So first of all, like we do for most dynamic programming problems, we're going to initialize our auxiliary, I cannot pronounce that, auxiliary DP array. It's going to be initialized to an array false times the length of our input string s. But there is a catch here. To account for our base case, when we're initially kind of populating our base case in our DP array, we have to actually get one more index so we have enough room to account for the base case and all the indices that come before it. So we have the length of s plus 1 to account or have room for that next index of our base case. So once we have this DP array initialized, we'll have the DP, again, this is our base case, at the index of the length of our input string s, the out of bounds index, to be immediately initialized to true. Why is it immediately initialized to true? Because since this is a base case, an empty string can always be segmented, right? It doesn't require any words to be segmented, and so that's going to be your base case, and we're going to use this to compute future suffixes for future indices using some various words of our word dictionary and rely on this computation or Boolean value true to actually futurely kind of compute more and more indices to check if we can actually effectively word break this problem up until the very initial index. Why do I say very initial index? Because we have to iterate over the string backwards, right? This is a bottom-up dynamic programming solution. So the way we're going to structure that is going to say for I in the range of the length of our input string s, but we have to start, the key here is we have to start from the last index. The last index isn't the length of s, that's one index out of bounds, right? That's the base case. We don't want to start from the one index out of bounds. We're going to get a list index out of range, and it won't make sense logically as well. We have to start from the last index in this iteration. So we're going to say for I in the range of the length of s minus 1, and we want to go up until the negative first exclusive index, or the 0th index, right? Because that's how for loops work in Python. I don't know why. And we'll decrement by 1 each time. We're simply going down by 1 index for every single iteration, right? Why do we actually have a bottom-up approach? Because we have to start with known values at the end, rather at the endmost of our input, or rather of our DP array, right? Where the end index is going to be the length of our input string s. That's our base case where we're going to initialize it to true to rely on that value to compute future suffix or index values, right? To check if we can word break it up until that index using some words of our word dictionary, right? Here we're just simply iterating backwards, starting from the last index, going until the 0th index of our input string s. And we'll have a nested loop here, so checking for every single word for this index I in our word dictionary. Okay, I really can't spell today. In our word dict. Okay, so again, for W or word in our word dictionary, if. The first case is if the current index I that we're looking at plus the length of the current word that we're looking at for this index I, if that's less than or equal to the length of s. So basically what that's saying is if it's in bounds, if we actually include or use this word dictionary from this current index I for this current segmentation, and s starting from index I, and this is some list slicing in Python, up until I plus the length of the current word W, if that's equal to our actual word W, meaning it has, or we're using this word from our word dictionary equal and so in bounds, then we can set DP at that index I. Well, simply to be DP at the index, or sorry, DP at the index of I plus the length of the current word to check if that's true, if we can actually segment it from DP at I plus the length of W, right, this index up until the end of the current length of the word W, then we can kind of use this word from this current word dictionary and go up until the index I. That's also segmentable. We're setting this Boolean value equal to what it was at DP at I plus the length of W, right? What does that mean? It simply means that if DP at I plus the length of W is true, then we can set DP at I also to be true, meaning that s up until the ith index, s from the ith index up until the end of the index can still be segmented, right? It can still be broken or word broken, right? And now we have to have another case. What's the other case? If the current index DP at I, if that's already equal to true, we don't want to compute for more values to check if we can actually segment this up until this index. We already know for a fact that we can already segment up until this index from the end of the array, and so we can immediately break from this iteration and move on to future indices, right? We don't care for other ways. We found already one unique way to actually make sure that we can actually segment our input string s up until this index I from the end of the array, again with that bottom-up solution, and so we essentially avoid unnecessary checks once we actually again confirm that up until this index from s at I until the end of the array, it's still segmentable. And ultimately, outside of this for loop, or rather nested for loops, we simply have to return our DP at index 0. Why do we return DP at index 0? It's going to tell us, is the entire input string S segmentable using various words from our word dictionary, right? So if we've actually made it to the initial index after iterating bottom up of all the different indices and checking if they're actually segmentable up until that index I using some words from our word dictionary, if this yields true, meaning we're able to segment up until the 0th index, from the 0th index up until the end of the array, right? So all of these, this entire input string is actually segmentable, then we can return true, right? Right? And as you can see, if I were to submit this, unless I made any syntax errors here, this should be accepted. And as you can see, it is just about as efficient as you can get. So I kind of want to just clear up some big questions that you might have. And when I actually started solving dynamic programming problems like this, I had these questions a lot. So I kind of want to clear them up for you guys if you kind of have them, if you're wondering why they're true. Okay, so why is the base case the length of S equal to true, right? Why is that? Because the fact that an empty suffix of S starting from the end is always going to be segmentable, and we have to rely or use that value to compute future suffixes from lesser indexes I as we bottom up iterate through input string S to see if it's segmentable from that index I until the end of our input string S. And why do we iterate backwards, right? The reason why is because, again, this allows us to actually build up our solution from smaller suffixes at the beginning, or rather at the end of our input string S, up until larger ones. And since dp at I depends on future states, like for example dp at I plus the length of the current word W, iterating backwards is going to make sure that those future states are already computed by the time we actually need them, right? We've already computed those values like we did for our initial base case of them right with the rightmost index at the end of our DP array, right at the length of the S index, right? And we're going to initialize that to be 0 like I talked about before. And this is going to be, again, like I said before, a bottom-up dynamic programming solution because we start with a known base case, right? DP at index length of S, and we initialize it to true, and we have to build our solution for smaller indices progressively as we actually move or iterate through the beginning of the string. Right? So for the time complexity, this is going to be a big O of n times n, where n is the length of our input string S, and m is the length or the number of words in our word dictionary. Why is that? Because the outer loop on line 5 is simply going to run for each index in I, or rather each index I in our input string S, giving it a big O of n, or linear time complexity, right? Again, where n is the length of our input string S. And the inner loop, index, or rather line 6, is going to be, for each position I, it's going to iterate over the word, or rather every word in our word dictionary. And if there are m words in our word dictionary, this is going to be a big O of m factor. And so total complexity-wise, this is going to be a big O of n times n runtime complexity solution. And for the space complexity, this is going to be big O of n. Why? Because the DP array is going to have a size of big O of technically n plus 1 for that extra index to account for our base case here. But that doesn't really matter. The simplified memory complexity is going to be big O of n, because again, coefficients and these extra constants don't really matter in big O complexity, right? So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.